Hello, and welcome back to the Scientific Ethics Lecture, where we're going to continue on our discussion of organ transplants. And so in the last set of lectures, we took a look at the human organ donation process, the limitations of opt-in versus opt-out programs, and the current state of organ donation within the United States, where we see a huge backlog of patients waiting on a list for an organ to become available, as well as kind of a number of people each day dying in the absence of an organ. And so that raises the question, are there alternatives to human organ transplants? Are there ways in which we can kind of repair the body in a way that's less invasive, or at least allows us to do this without the requirement of organs coming from other individuals? And so, again, keep in mind that when we're taking a look at, we talked about this when we take a look at how the body works, generally we're not looking at transplantation of organ systems, we're looking at transplantation of organs within the system, or potentially tissues or cells or molecules. And so damage to any of these could result in deficits in the body not working properly, and can contribute to a disease state. And so what we want to do is try to repair whatever is broken here in a way in which we can treat the disease. And so an example of this is going to be diabetes. If we take a look at what's occurring within a patient that is healthy without diabetes, what we're going to see is that there are going to be these kind of bluish cells, which are going to be found within the pancreas, which we haven't talked about in this course, but the pancreas is this organ kind of sitting right here, kind of sitting here between your liver and your intestines, kind of right around the stomach, kind of behind it here. And this is going to be an organ that's important for making digestive enzymes to break down your food within the intestines, kind of down here. But it also secretes hormones. And one of the hormones it secretes, these beta cells, these bluish cells here, they're going to secrete insulin. And so basically what that insulin does is regulate the sugar levels within your bloodstream. And so what's going to happen is you have a good hearty meal, your body starts to digest that food, the sugars are brought into the body, they get into the bloodstream. And the problem is that having too much sugar in the blood can cause a lot of problems. Contribute to diabetic ketoacidosis, can kind of disrupt the blood flow, cause nerve damage, cause blood vessel damage, unless we can bring that down. So in a normal, I don't want to say normal, in a patient without diabetes, with a normal functioning hormone secreting cells within the pancreas, as those levels of sugar start to rise within your blood, these cells release insulin. That insulin goes out to the body, basically says, okay, we got all of this sugar available. Anybody that wants it, take it, use it, store it, it's available to you. And the process of that brings down the sugar levels to what it needs to be. They control the sugar levels within the blood. In patients with type 1 diabetes mellitus, they basically aren't producing insulin. They don't producing enough insulin. And so what that means then is that they can have a good hearty meal, and that level of sugar can stay high within their bloodstream, and it could cause potential damage to their cells and damage to other regions of their body. And so for some people, they can have a strict diet with limited sugar intake. They can regulate it, by diet and exercise in essence. But over time, it becomes harder and harder to regulate. And so they basically have to have insulin to control the sugar levels within their blood. So if we take a look at this, and this again, going back about 100 years, a lot of this is going back about 100 years in this course right now. What two scientists, Banting and Cloud, discovered is that they could isolate a protein called insulin. It's going to be a hormone. They could isolate it from fetal calf pancreas. So, they go to a slaughterhouse, collect the pancreas, isolate the insulin, and they could use it to treat diabetic patients. They could take this insulin from a calf, put it into human patients, and be able to regulate the blood sugar levels within the patients and keep them healthy. Eli Lilly is a pharmaceutical company. They basically went into large-scale production of insulin from pancreas, extracted in about 1923. And for about 60 years, this was the predominant source of insulin for the treatment of patients with diabetes. Now, if we think about this, basically, they went from cows and calves to pigs as well. They were basically collecting cow insulin or pig insulin. They go to slaughterhouses, collect the pancreas, isolate it, and then make it available to patients with diabetes. And this was the only source of insulin till about the 1980s. Some of the recombinant DNA technology we'll talk about later on within this course. In the 70s, they discovered how to clone insulin with terms I'm not going to describe until later on in the course, but they basically were able to make cells, bacterial cells, produce human insulin as opposed to cow or pig pancreas insulin in a method using some DNA technology, some kind of new science methods. Now, if we take a look at this, animal insulin, either a cow insulin or a pig insulin, is not exactly the same as human insulin. And so for some people, again, keep in mind what we were talking about with the need to match an organ donation with the recipient. For some people, they would mount an allergic reaction to the animal insulin. And so they couldn't take pig insulin. They couldn't take cow insulin without being harmed by it, without triggering an allergic reaction and making themselves sicker. And so the goal was to become a way to develop human insulin. And so probably lots of ethical issues concerned with going around and collecting human pancreases, grinding them up, because we don't have the ability to do that like we would do with, a cow slaughterhouse or pig slaughterhouse. And so we needed to be able to do it with DNA technology to get us that human insulin. And so that human insulin is not allergenic. And so that was a very important kind of breakthrough. But that again gives you an idea. Go back a few slides. In that case, the cells weren't working properly in a patient with diabetes. We figured out what molecules were important, that molecule being insulin. We provided it by pig and cow pancreas initially, and then used DNA technology to produce human insulin for a period of time. So again, this is similar to tissue donation, but we're not donating the tissue, we're not donating the cells. We're basically isolating the molecules that are needed, the hormones that are needed, and treating it that way. To take another example, we can take a look at blood cell diseases. Blood cell diseases like leukemia. Leukemia is a cancer affecting blood cells in the bone marrow. Lymphoma is a cancer affecting the immune system cells, the cells that kind of protect the body from bacteria or viral infections. So, if we get a cancer of that, they're going to spread through the body and cause problems. Aplastic anemia is a disease of bone marrow where it doesn't produce enough red blood cells. And if you don't have enough red blood cells, you're not going to have enough oxygen being transported within the bloodstream. So in all three of these instances, we've got different disease processes affecting either the cells producing blood cells or the blood cells themselves. And so if we take a look at this, we want to try to replace those dead or damaged cells. And so there are a couple sources that we can come about. You can do a bone marrow transplant. And so you basically kind of go right into generally like the hip bone with a big needle, draw off some of the cells that are going to be producing blood cells. And again, if you've got a donor match between the donor and the recipient, you can then take these bone marrow cells and inject them into a recipient and hopefully reestablish or reseed the cells that are needed to produce a good, strong circulatory system. There are some ways in which you can do it from peripheral circulating blood. And so you basically go in as if you were going to be doing a blood donation. And they've got a special machine that kind of isolates the cells that they need from the circulating blood. Or more recently, there are going to be specialized cells within the umbilical cord that can be harvested and grown and used as a source for these cells. And so what we've seen over the last 10 or 15 years is a greater movement for kind of collecting the umbilical cord and collecting these cells in case the the newborn that is born with that umbilical cord needs those cells later on. And so these are kind of a variety of sources. So, the bone marrow, the peripheral circulating blood, again, you need a match between the donor and the recipient. The idea is that if you've got this umbilical cord blood, you've got it from the patient themselves in case they need it at some point later on within their life. And it's, coming from their own umbilical cord, and so they would be automatically matched up with their blood, and they wouldn't have to worry about potential rejection or kind of damage because they're mismatched in getting these cells. Okay, so if we take a look at this, again, with the bone marrow transplant, generally what we're looking at is some type of cancer that's affecting these cells, so that after a donor has been identified, the patient has to get rid of all of those cancerous cells. And so these patients are often going to go through kind of chemotherapy or radiation therapy that's going to go through, kill the cancerous cells. It kills all kinds of other cells within the body. So it's a big hammer to treat this. So they have to make sure that they got a really good match with the donor is healthy and is going to follow through on it, because once they start this treatment, they're going to go through and destroy the blood forming cells, they're going to destroy the cells forming the immune system. So if they don't get the donation after they start this process, they're going to be in a really bad situation because they've really damaged their blood system. So normally what happens then is they're going to take the donor cells, almost put it into an IV or inject it into the bone marrow. But in most cases, they just put it in, circulates through the body, and the cells are going to get into the bone marrow in most cases on their own, and hopefully then become established and kind of establish the kind of production of cells that are needed within the body. And so again, this is important because in this case, we need to have that good, strong match between the donor and recipient, because in some cases, we're going to be mounting or creating a new immune system. And so those donor cells are going to go into the recipient, establish an immune system. And if we don't have a good match, it's not going to be the immune system of the patient attacking the grafted cells. What we're going to have is what's referred to as graft versus host disease, where these donated cells are going to get in and basically attack the rest of the body. And so incredibly, incredibly important that we have a good match. But if we have a good match, this could potentially heal that patient, and they're going to be still probably taking cyclosporin, some of those immunosuppressant drugs, but they're going to be in a much better situation than when they had the blood disease. Another example is taking a look at kind of mechanical valves that can be put into, in this case, we're taking a look at the heart. So you can see the heart pumping, you've got the valve here, blood flowing through, the valve slamming shut to keep the blood moving in the right direction. A couple problems with valves. You get regurgitation if the valves don't close properly, blood will flow backwards, and you have a blood murmur. Not blood murmur, a heart murmur, and you can hear that. Sometimes you'd have a stenosis, like a thickening or a disruption to the valve itself, so it doesn't open properly, and it disrupts the blood flow. And so a patient is going to have heart problems because of a defective valve. It's very difficult to do a human-to-human valve transplant. Often they would do it with a mechanical valve or another mechanism. And so if we take a look at it, a mechanical valve, we've got a couple of examples of it here. These are man-made, so the idea is that blood kind of flows through, pushes this little ball thing down as the heart is contracting, and then once it's done contracting, this pressure is going to build up over here, and that ball is going to slam back and close it. They're designed to be long-lasting. They're made from stainless steel, titanium, ceramic in some cases, so they last a long period of time. But the patients with this are often treated with blood-thinning medications so that blood doesn't kind of clot onto these mechanical valves. And so they'll take things like Coumadin or aspirin, which means that they're susceptible to bleeding for taking these blood thinners, but they've got a heart that's functioning properly, a valve that's going to be functioning properly. And that finishes up the first half of this. We'll be taking a look at a couple different alternatives to human organ transplants. Come back for part 2, we're going to take a look at xenotransplants. I'm not going to define what xenotransplants is, so that you have to come back and find out. As always, if you have any questions, feel free to email me. Thank you and have a great day.